Alrighty, guys. Welcome, Chemistry Montessori. This is Mr. Aragon, and I will be going over phase change and energy, that worksheet that you have that's due on Monday. This hopefully should be a brief video. I'm not going to do the entire thing. I will just give you a couple of scenarios, fill out a couple of these, and then basically let you go from there on out. Okay. First things first. If I'm a student in Montessori, right? The first thing and possibly the most important thing that you could do as it pertains to completing homework is write your name. So, of course, my name is Ulysses Aragon. All right. Most important thing, because if you want to get credit for your work, you have to write your name on it because I don't like chasing kids down. All right. Energy. Energy is the ability to do work. I pretty much gave you this definition. There are two types that we deal with. We're going to deal with kinetic energy, which of course is energy that is moving. So when I think of kinetic energy, I think of kicking, because kicking is movement. And movement is kinetic energy because kinetic energy is energy that is being moved. I want to give you guys another example. Remember, average kinetic energy is equal to the temperature. So the average kinetic energy of molecules, right? If these are gas particles, and I'm going to draw arrows to signify their movement. The faster they move, the more kinetic energy they have, which means the higher the temperature. So when we say average kinetic energy, it's the same thing as temperature, right? When we take the temperature of something, we're taking the average kinetic energy of those molecules that are moving inside, right? Potential energy is stored energy, right? So if I have my pen here and I lift it off of the paper, it has the potential to do work, right? It has stored energy. When I drop it, it is kinetic energy because it is energy in motion. Now keep in mind, if I have my pen here, I have potential energy. If I raise it up a little bit, I have more potential energy because the higher I go, the more energy it's going to have, the more kinetic energy it's going to have. Okay, awesome. So phase changes, right? Think of ice versus water versus steam. When I go from a solid to a liquid, for example, ice to liquid, the name of the phase is called melting, right? The point at which it changes is typically called the melting point. Right? Okay. When I go from liquid to solid, so when I go from water, or I'm sorry, yeah, when I go from water to ice, I'm doing freezing, right? The phase change is called freezing, and that, of course, is called the freezing point. Okay, from liquid to gas, you guys can figure out what that is. When I go from water to steam, when I go from gas to liquid, that's called something, right? I'm going to skip that, let you guys figure that out. Endothermic. So endo, we deal with two types of energy here, right? Or heat transfer. So endo, I think of N as in. Heat goes in a system, right? Heat goes in. Feels cold. Exothermic. Exo, I think exit. I'm tempted to say Enzo. Ha. So exothermic, heat goes out, right? Heat leaves and it feels hot. Perfect, right on. Okay, so I'm going to give you a little example here. Your car burns gasoline as you drive. So if you have, I'm going to say, a container of liquid gasoline, right? If you add heat to it or a spark, This gasoline will burn and it releases a ton of heat. This is exothermic, right? Because the heat is leaving. When I think of endothermic or exothermic, I'm not thinking hot or cold. I'm thinking of where the heat is going. It's going from inside of this system to the surroundings, so it's leaving. So this is exo. Ooh, Jerry is baking homemade bread in the oven, right? So if I have a fat piece of dough in an oven, right? Heat, in order to bake the bread, heat is going from the outside to the inside. So heat is going in. Heat in. So if it's endothermic, or I'm sorry, if heat is going in, it's called endothermic. Right? Ice melts in your glass of water. This is a tricky one, right? Good old cube of ice, water, right? So in this scenario, the water is actually going to be hotter or have more heat than the ice, right? So in order for the ice to melt, heat has to go in, right? So this is endothermic. Awesome. Okay, let's see. I'll let you do these actually, the rest of them, so you guys should be good. And keep in mind, if you guys don't have this down and you guys need additional help, like I said, Miss Nguyen is a phenomenal teacher, and she will most likely be willing to help you guys out. If you opt out and you decide to do this at home and you realize that, holy moly, I don't understand what's going on, you can always email me or reference the YouTube videos on your work plan. So now let's get into this phase change diagram. We've talked about this before, which is cool because now we're doing it again, except now we're adding a little bit more meaning, right? So on the y-axis, temperature in Celsius, and it increases as it goes up, right? On the x-axis, it's heat, and it increases from left to right, okay? I'm going to fill these in for you guys. So solid, liquid, gas, right? That's what we learned. If this is water, this would be solid, liquid, and gas. And that makes sense, right? If from A to B, a substance is solid, but if I'm going from A to B, I'm increasing the temperature. I'm adding more heat, right? If this is heat, right? I'm going to give this as an example, like 1, 2, 3 or something like that, right? If I'm going from A to B, I'm increasing from 0 to 1, right? Or something like that. Cool. So I'm increasing the heat and I'm also increasing the temperature. Well, when I get to B, this is actually the melting point. Right? And from B to C, the object is melting. Right? So you'll notice that from A to B, you increase the heat and you increase the temperature as well, right? And then from B to C, you're not increasing the temperature, right? Because you're using so much energy to continue to melt the object. And once it hits C to D, it increases in temperature and it's now a liquid, right? From D to E, you're actually evaporating. You'll notice that if you go from left to right on this x-axis, you're actually adding heat. So when you melt something or when you evaporate something, you're adding heat, so therefore it's going to be endothermic. Now, when you go this way, like when you go from gas to liquid and you condense something, you're actually releasing heat, right? So this would be exo. When you go from liquid to solid, or when you freeze water, for example, you want all that heat to leave, right? So you'll notice that you're actually reducing the amount of heat in the system, and it's releasing out into the surroundings. So this is exo. And that makes sense, right? If you want to make an ice cube, you want all that heat to be out. Awesome. So now, from A to B, is it endothermic or exothermic? Well, we just got done saying that if it's going from left to right, if you're adding more heat to the system, right? You're increasing the heat. So this one would be endo, right? Ooh. So what's happening to the, and I'll give you an example here. What's happening to the kinetic energy, right? So remember, kinetic energy, or you could say average kinetic energy, is the average of the kinetic motion, or of the movement of the particles. So you'll notice that the faster the molecules move, the higher the temperature, right? So you know that if you're increasing the temperature, you're increasing how quickly those molecules move. So you're actually increasing the kinetic energy, right? Perfect. And for potential energy here, I talked to a couple students about this. You can go about this whatever way you'd like, right? You can say that there is a loss of potential energy because when you increase kinetic energy, you actually lose some potential energy. But what you can also say is that some of this potential energy, once it reaches B to C, it's actually increasing, right? Because this is the same thing with the pen. If I'm down here, I have potential energy, but if I move it up, I have more potential energy, right? Same thing with this graph. All right, so let's do from D to C, right? So from D to C, right? You're going basically from evaporation. You're basically going from a gas to a liquid, and you're decreasing the temperature here, right? You'll notice that from this point to this point, your temperature is going from this point to about that point, right? So you're actually decreasing the temperature. So what you're doing is you're releasing heat, so exo. And then what's happening to the kinetic energy here? It's actually decreasing, because when you cool something down, you're actually causing those molecules to move much slower, and you're decreasing the kinetic energy. So this one would be decreasing, right? Perfect. All right. I'm going to fill in those 4 for you guys and let you guys kind of take it from here. Like I said, if you guys have any questions, please email me, or please get in contact with Miss Nguyen. She will definitely help you guys out. Okay. Thank you guys for watching.